Hi, and welcome back for a few more bits of advanced SQL. Okay, so the last time we focused on row variables, row types, and row values. Let's now focus on the big three constructs that make up a SQL query: the select, the from, and the where clauses. Okay, so let's get these out of the way to move on to the more interesting stuff. The select clause, the very first clause syntactically in a SQL query, but actually one of the clauses that is evaluated last, interestingly, is simply listing n expressions. N expressions, E1 to En, and all of these expressions are evaluated and then together form a row of n fields. The values of the n fields are computed by these n expressions. Okay. The names of these n fields, we are constructing a row value of n fields, and the n fields should have names. These names can be assigned using the as syntax. Okay, so in this case, we are not introducing row variables as in the from clause, but we are introducing field names. So the first field of the row that we are constructing here is to be named C1. The last field is to be named Cn. Okay, so that generates a row value with n fields named C1 to Cn. Again, you may omit these as Ci specifiers, and then PostgreSQL will come up with its own name for these particular fields. We are constructing a row value. The fields must have a name, so in the absence of you giving them a name, PostgreSQL will assign a default name, and that default name is ? which is a really bad name. And it's particularly bad because all the unnamed fields will receive that name. So the row value that comes out of this computation will have quite ambiguous field names. Accessing one of these particular unnamed fields will be difficult because all of them will share the same name. That's really bad style. So the Frony is in place here, I would say. So again, in this course, I will try to make sure to live up to good SQL style and always explicitly use the as clause in the select construct to explicitly name the resulting fields. Sometimes it's really not necessary because sometimes PostgreSQL or the SQL language is capable of inferring good names on its own, particularly if the expression that we are computing has a shape like this. So we are projecting on a particular row variable the field A, and the convention in SQL is that the resulting field and the result will also be named A. In this case, we could write t.a as A, but that the as A would be superfluous in this particular case. In these cases, SQL is able to invent proper names itself. Otherwise, it's really good style to use these explicit as Ci clauses. Okay, these named Ci can be really funky and really unusual. If they are funky and unusual, and sometimes there is a good reason for that, then you can do that if you enclose these names in double quotes. So single quotes are used in SQL to specify string values, textual values. Double quotes are used to introduce funky names. Funky means we could have white space in this particular name Ci, or some Unicode symbols. We could even use keywords. Sometimes it's desirable to have a column named from, a field named from. And from is a SQL keyword. We can still name a particular field from if we enclose the word from in double quotes. Okay. So a select clause in such a SQL query is evaluated many times. For each binding of row variables that the query is creating, the select clause will be evaluated once and generate a resulting row, and the result will be a table of many rows in general. We will come back to this when we are looking at the from clause actually. But there is the syntactic possibility to just have a standalone select clause, no from inside anywhere. In this particular case, the select clause is evaluated exactly once. So exactly one row will be generated in this particular case. And we can make that, get use of that, good use of that to use or abuse SQL as some sort of pocket calculator, for example. So that would be a SQL select clause without any from clause, a standalone select, and it will compute a row of two fields, first field, second field. The first field will contain the value 42, the second field will contain the value GLaDOS. This is string concatenation in SQL. Okay, and these fields will be named. This is a funky name containing white space and containing upper and lowercase characters. Double quotes will preserve the white space and they will preserve the case. So indeed, the first field of the answer is the answer. All right. Here, no quotes are used. So in this case, SQL performs some name normalization on these names, and as you can see, that everything is normalized to lowercase. So portal in this case comes out as lowercase portal in the result, but otherwise it's just the name that we were expecting. Okay, so standalone selects, and here using as clauses to introduce explicit field names. Had we omitted the field names, back to our SQL console here. Okay. Let's just rewrite the query again and evaluate that. Okay. Then the result is okay. It's a row. It's one row of two fields, but both fields are named question mark, column, question mark. That's really questionable. Okay. So use explicit naming to reflect the meaning of the contents of such a column or such a field of a row, and to make your queries more readable. It's considered good style. Okay, so before we come to the from clause, let's talk about the clause that is normally not often seen and not often used. It's the values clause that is being used to introduce constant tables, literal tables. So it introduces the data structure, the main data structure that SQL is known for, namely operating over tables. And of course, SQL comes with a syntax to let us specify literal constant tables inside queries. And the construct that we are using for that is the values clause. And the semantics and the syntax of the values clause is really simple. Because we want to construct a table, a literal table, it will be comprised of many rows, and we just specify the row values that will be collected in this particular table in a comma separated list here. So these E1 to En, these are used to specify n row values. If we actually build a table of more than one row, so if n actually is larger than 1, then of course all the rows here must have the same shape. They must have the same number of fields, for example. And inside the fields there must be values of compatible or the same types, because all of this is to be collected in one homogeneous table. So all of the rows have to have the same number of fields, and all of the rows have to have compatible types. And the first row value E1 here is special. It is used to determine the number of rows and the field types of these of the individual fields of this particular table. E2, E3, and all further rows have to comply with the number of fields and the field types introduced by E1. This is a literal table. It does no table heading or a separate schema whatsoever. So the values clause has to resort to some automatic column naming here in this sense. So the first column will be called column 1. The last column in this case will be called column n. These again are really bad column names. At least they are unique. And we can make up for that and then later rename the columns introduced by the values clause using the from clause, and I will show you how to do that below. Okay, so values introduces a literal table, and SQL indeed allows us to use a values clause wherever a query would normally expect a table. Normally you would probably expect a named table in such a query, but we could equally well use a values clause to specify such a table. It's a syntactic convention or syntactic necessity to then enclose this values clause inside parentheses. So a values clause inside parentheses is as good as any table and may be used in SQL queries wherever a table is expected. For example, in the from clause, and we'll be seeing that shortly. But first, let's play with some values clauses. I brought one values clause with me. You see, I've used one comma in this particular values clause. So here's one row, here's one row, though. So this values clause will introduce a literal table of 2 rows. Because they are of 2 rows, both of the rows have to agree in the number of fields. They do. They both have only one field here, and these fields have to agree in their type. They have to be of compatible type. Both of these fields use integers. That should be fine. So let's see what the evaluation of this clause brings. Okay, so a 1-column table is constructed. The first column in the absence of any proper naming is called column 1, and of course 2 rows with values 1 and 2 here. As you know, the order of the rows here is completely arbitrary. In this case, it reflects the order of the query, but it might be just the other order around. Another values clause would be this. So this introduces a single row value of 2 fields and nothing else. So the resulting table will have 2 columns, but only a single row. Yes, indeed. 2 columns, 1 row, and the columns are named as I told you on the slide. These temporary names have been introduced that we can later then rename as we like. Okay, and a larger values clause would be this. This would introduce 2-column row values into a 3-row table. All of the types are compatible. We only have booleans in the first column. That would be a boolean, a null value of type boolean. That would be a null value of type integer, because the first row value has prescribed that the first field must be a boolean, the second field must be of numeric or of integer type. Let's evaluate that, and that would give a 2-column 3-row table as expected. 2 null values in this particular row. We could try and violate some of the conventions or some of the necessities that we've been introducing. For example, we could work over incompatible types. So single fields but incompatible types. Let's see what's happened here. Okay. So SQL is complaining that this X is not a valid syntax for an integer. Why integer? Because the first row has introduced the need for integers in this first and only field. We need integers here. Okay, so let's do that. Or we could supply integers, but maybe change the number of fields here. So this cannot be put into one homogeneous table of 1 or 2 columns. I don't care. I don't know. So SQL will complain again. All the values, all the length of the row values must be the same. Okay. So literal tables. Okay. So the second core clause in such a SQL query is, of course, the from clause. And it's the from clause that will introduce row variable bindings that we can use in further expressions, for example, in a select clause, to compute further intermediate results in our queries. So this is the role of the from clause. Introduce row variable bindings. And the from clause has the ability to not only introduce bindings for one particular row variable, for example, row variable t1, but for a whole set of row variables. So we can introduce n row variables t1 to tn here, and they draw their bindings from their associated n tables. And you can see these n tables and their row variables are separated in a comma separated list. These are tables, and of course these may be named tables that we are storing in our database, but they might as well be values clauses as long as we enclose them in parentheses, as I told you. And we will see that in an example shortly. Okay, so if we are indeed using a values clause in this particular spot, then that values clause is supplying very poor column names, very poor field names, column 1, column 2, column 3. So here at this point in the from clause, we have the ability to not only introduce row variable names, but also rename the fields to our liking. We can rename the fields of such a row value bound to these row variables to our liking. For example, we could rename the column 1, column 2, column 3 fields introduced by the values clauses to some self-speaking, unambiguous names that make sense in the rest of the context of the query. And the syntax is really simple. At the point where we're introducing the row variable, we will do that as always. And if we append this comma-separated list of field names in parentheses, then we have the ability to name the first, second, and the kth field here to something that makes more sense in the context of a query. So this works for any table on the left-hand side here. For a values clause, for built-in tables, we can rename the field names when they are bound to a row variable here in the from clause. This is called column aliasing. And it's good style to really explicitly rename all the fields so that the query is really speaking for itself, and we can read off the field names, the now current field names for all the fields here in this column alias clause. Unfortunately, SQL syntax allows us to only rename the first k or the first few columns, but I think this is bad style. If you use column aliasing and rename field names, rename them all at once. So let's see how this could look like in a SQL query. That would be such a SQL query, having a select clause and a from clause, one single from clause. And here we have used a values clause inside parentheses to specify a literal table. It's a 2-column table of 2 rows, so T will receive 2 row variable bindings. The fields of this literal table will be called column 1 and column 2, and we are not using column aliasing here. So T will be bound to 2 row values with the field names column 1 and column 2. And as you can see in the select clause, we are requesting the output of all the fields of row variable T, and these fields will be named column 1 and column 2 as we are not doing a renaming here, and that's what we get. Okay, so column aliasing would work like this. At the point where we're introducing the row variable, we will also rename the column names here. Let's name the first field, the first column, truth, because we are storing Boolean truth values here. And the second column, let's call it binary, because it obviously stores binary values 0 and 1 here at this particular point. And because binary is a built-in keyword into SQL, this is considered a funky name that has to be enclosed in double quotes. But as soon as we do that and evade this query, then we get the same result, but with explicitly very well named column names or field names in this case. Okay. Whenever a from clause mentions more than one table, as in this example, where we have n of such row variables introduced. Then, as you probably know from DB1 or any other introduction to SQL, then the semantics of the from clause is to produce the Cartesian product of all possible bindings. So T1 will be bound to a row of T1, of table T1, and that binding will be fixed, and then we'll produce all other possible bindings for the row variables to T2, T3 up to Tn. Then for the next possible binding of T1, we will reiterate and again produce all possible bindings for all remaining row variables here, T2 to Tn. So in the end, we will end up with the Cartesian product of possible row bindings. How many row bindings will there be? Well, possibly many. If this is the cardinality of the first table, this is the cardinality of the last table, then we get a product of the cardinalities of all involved tables here. This can be a lot, even if the participating tables themselves are not that large. A Cartesian product can blow this up, and the one from clause might generate quite a number of row variable bindings here. Okay. It's important to note that this comma here, this comma in the from clause, okay, let me highlight that. I'm speaking of this comma here and this comma. This is actually a commutative comma. Whether I put this T1 as T1 clause first here or last or at any other place inside the from clause is really immaterial. It will the same row variable bindings will be generated. The same number of bindings will be generated. This comma really is a commutative comma. You can rearrange the clauses in the from clause to your liking, how the query reads best, how the query is best formatted in your editor. Choose any order that you like. The system will choose a particular evaluation order on some well-defined criteria that are not related to your syntactic conventions of naming T1 first and T1 last. So the comma is really commutative. The system will internally rearrange the order of the iteration over these tables anyway. Okay. This in particular makes clear that there is no such thing as the variable T1 to be visible in this or any subsequent row variable binding. So the variable T1 introduced here is not in scope in the rest of this from clause. It's just not to be seen there. If this is a complex expression that computes a table, this expression will not be able to see the bindings for this row variable T1. Okay. This is something to be remembered, and we will come back to that because it's an important point in specifying SQL queries. Of course, row variable bindings for T1 could be used in other parts of the query, for example in the select clause in one of the expressions E1 to En that we can specify here, but the T1 is not visible in the rest of this from clause. Okay, so and the third and final clause of the big three in a SQL query is the where clause. And the where clause specifies a single predicate P, that is capable of throwing particular row variable bindings away. Only those row variable bindings that make predicate P true. Predicate P is a Boolean expression. Okay. Only those evaluations of the predicate P that yield the Boolean value true will be considered positive, and only those variable bindings will pass this predicate filter and then actually be passed on to the select clause for evaluation. So the evaluation order in fact is this: first establish all the row variable bindings, then check to see whether these bindings can make predicate P true. If this is the case, only then is the select clause evaluated last. So the syntactic the syntactic convention of writing select first, then from, then where might be a bit misleading, because the real evaluation order is from, where, select. Okay. Of course, in P, in this predicate P, all the variable bindings of these row variables are in scope. We can refer to these bindings to decide whether this is a binding that should be able to be passed to the select clause, yes or no. Only those bindings that yield true are actually passed on. You may omit the where clause, and that's the same as writing where true in this particular case. True is the trivial predicate. It is always fulfilled. Any binding will pass. So in this case, instead of writing where true, you could just omit the where clause entirely. Okay, so let's switch back to the editor and see what we can do with these constructs. Okay, so that would be a select from clause, a query without a where clause. So there is no filtering going on, but there's a Cartesian product going on. Okay, so table T is involved 2 times here. Okay, so row variable T1 will receive 5 possible bindings. Row variable T2 will receive 5 possible bindings. All of the combinations will be actually generated, so we will receive 5 times 5, that is 25 row variable bindings that will be generated for all combinations of rows extracted from tables T and assigned to row variables T1 and T2. And because we are outputting all the fields that row variables can contribute, for the second row variable we use column aliasing to make the field names unique. So the output will look like this. That's quite some output, 25 rows as expected. Okay, yes, okay, and 8 fields. Each of the row variables can contribute 4 fields. The second row variable here contributes the renamed fields A2 to D2. Okay, and for this particular binding of row variable T1, we find all possible bindings. Let me mark this. We find all possible bindings for T2. That makes for 5 bindings already. Okay. For all bindings of variable T1 to this particular value, we will find all possible bindings for T2. Okay. And so we end up with 25 rows, the Cartesian product of all possible bindings in this case. Okay. So let's mix stuff a bit and build a Cartesian product of 2 tables. One of the tables is literal table. A literal table that only contributes 2 rows. 2 rows of textual values. I've used these circled 1 and 2 symbols here to really make sure to really display which of the 2 rows are actually taking part in the Cartesian product here. One of the row variables is called 1, 2, and I'm using column aliasing to rename these unnamed fields, or these fields column 1, column 2 to num. Okay, all right, so let's evaluate that. That should yield 2 times 5, that is 10 possible bindings. Each binding for T should be accompanied by 2 possible num values derived from this first literal table. Let's evaluate that. There you go, 10 rows generated. Okay, so for this one binding of row variable T, we find the 2 possible bindings of the num field. And that's the case for all of the possible row bindings that we can generate for T. All of them occur twice with their associated binding for the 12.num field. Okay. And the where clause could then be used to reduce the quite large output that this from clause is generating to something smaller, to only the interesting fields, rows. I'm sorry. So, for example, that would be a predicate that refers to the num field of the 1, 2 variable and would let only pass those bindings for 1, 2 in which the num field is actually the second circled 2. These bindings will be discarded. So that should generate 5 possible bindings, I would say. 5 possible rows. 10 bindings, but only 5 possible output rows, because half of the rows, those with 1, 2 num bound to the circled 1, are being discarded by the predicate. Okay. So a closer look at the where clause. These predicates can be quite complex. For example, we could have comparisons where the left or the right hand side use arithmetic expressions. So only output those rows T for which the A value is, or for which the D value is 10 times the A value. Okay, let's see whether we can do that. Okay, there's 2 such rows. So A times 10 is 10, 3 times 10 is 30. Looks good to me. These are the only rows that may pass under this particular predicate. Okay. Boolean columns. Boolean columns are particular, make for particular predicates. So this is already a Boolean value, and the value in itself could already serve as a predicate. So let only those bindings pass where in the C column, that's the Boolean column, we will find a true value. Okay. And that's what we see here. So in 3 of these C columns, in 3 rows for these C columns, we find a true value. These are these are exactly the rows that we will see in the result here. I could have written this where clause in this particular fashion, but it's an abuse of comparison with Booleans, I would say. That's a no-go or bad style, I would say, that is also often found in programming languages. Try to avoid that. This is already a Boolean value that you can use as a predicate. This is also a possible predicate. Only output those rows which feature a null value in the D column. I think there should be only 1 row that qualifies here. Okay, only 1 row qualifies. D indeed is null, and all the other 4 rows of table T have been discarded. All right. So make sure if you compare with null, we have said that before, to use the is keyword to perform comparison with null. If you don't do that, if you use the equal sign, the following is what you will get. So here I've listed the D value, and I've listed here in this column the comparison of the D value with null using the is keyword. And indeed 10 is not null, and 40 is not null, and null is null, and that looks good to me. A comparison with the equal sign of such a TD value with null will always yield null. This operator is not prepared to compare its left-hand side with the null value. It simply cannot tell whether the left-hand side is equal to the right-hand side. The right-hand side null represents anything unknown, and the equal sign can actually not tell whether the left-hand side is equal to something unknown. The outcome of this comparison is thus unknown or null, as you can see here. Okay, so comparison with null, please use the is null construct. In particular, this null value here in this case is unknown. The unknown Boolean value, and it would not be true. It would not be false. So the where predicate would not let such a binding path in this particular case, because this is unknown and not true. Okay, and a more complex example would be this last example, where we draw bindings from this Cartesian predicate. We will draw bindings T1 and T2 from our playground table T, and then let only those combinations of bindings pass. Let only those row variable bindings pass where the a value in the first row variable is in a range between -1 and +1 of the a value of the second variable. All right, so the a values of these two row variable bindings may differ by at most 1. Okay, if they do, you as a binding you may pass, and we will evaluate the select clause, and you can see that the select clause will generate two fields, the a field, the t1.a value, and a concatenation of the b values, the b string or textual values that are contributed by the two row variables. And that is the row variable, the column name, that the field name that we will be choosing in this particular case. So let's evaluate that. Okay, so that's a two-column table as expected. These are the a values that are being output in this case, and these are the concatenations of the string values, of the x and y string values contributed by the two row variables. We could make the select clause a bit wider here and then check whether the a value of t2 is indeed in the expected range of the t1 value, so it differs by at most 1. Let's re-evaluate the query and check. Okay, so 1 is equal to 1. 1 is differs at most by at most 1 from 2. Looks good to me. 2 differs by at most 1 from 1. Looks good to me. So only acceptable row bindings have passed this predicate, and we see the expected output. All right. So these are the big three: the select, the from, and the where clause, and how they interact with row variable bindings, row variables, and so on. The other big clause that we've introduced is the values clause, the literal table clause, and I think it's a very important clause because it introduces values of the data structure, namely the table in SQL, and a query language or any program language would be incomplete without the possibility to introduce such literals or such constants. Okay, so even more stuff to play with in the upcoming lectures, and I hope you stick around. Be seeing you soon. Take care and bye-bye.